have fluid to deal with. Okay? Let's go back to that original structure. Where I'm going to have those frequencies, that sound energy, move into my outer ear, meet the membrane. And that's going to cause that membrane to vibrate. And when this happens, it causes these inner ear bones to move, the one of which is at that oval window. The oval window, do you happen to remember where it meets? My inner ear at the point for fluid. So now that stirrup gets to knock on that oval window. What is that going to do to the fluid? We're going to move. It's going to start like a wave action in my endolymph. And my endolymph has connection to nerve fibers. So now that fluid is moving through that cochlea over that entire structure. And by doing that, it's actually causing a reaction to occur in the cellular structure. Is everybody kind of seeing how this happens? So if I take this structure, which is going all the way through that cochlea, and if I have this makeup of it going all the way, all these little cilia get to move. Is everybody with me? So that fluid gets to push on those cilia. When it does, because of their structure, what do you kind of note about the number of cilia to one cell? There's more than one. We have several cilia to one cell connected to a nerve fiber that is going to make its way to, in this case, since it's the cochlea, the cochlear portion of that nerve. So this structure that you see right here, it kind of has a structure like this, where you got one that's short, one's a little taller, one's a little taller, okay? And they have little links between them. So if that fluid begins to move, it's going to push on these cilia, and because they are linked together, that pulls all of them. And by doing that, the makeup of the fluid, which would have ions, pluses and minuses, okay? Because it would have ions, they get to rush in and they get to start a action potential on the nerve fiber. And then we hear. Is that pretty cool? Or is it just me? So, as that structure because, like I was saying, the structure begins to be what it's important. If you look back, they have what they call the superior and inferior chambers. You see how when they cut it open like this and cut it open like that, they consider one to be superior, one to be inferior, okay? And they gave them names. Scala, I think about a scale for music, okay? So they've got one that's upper, one that's lower, and then we, of course, got the middle chamber, which is going to have our endolymph and the cochlear duct that's present. We get that separation because we have to keep a chemical difference. Do you remember about action potentials? Action potentials were dependent on one ion being greater on the outside than the inside of the cell. All right, same thing here. So having the perilymph and the endolymph, I'm keeping a little bit of electrical difference so that I can start that electrical impulse on that nerve fiber. So what we'll see, okay, the cells that were present, because we're going to find we have our supporting cells, and then we have our cells of hearing. They're referred to as hair cells. Okay, y'all ever heard that term for the hearing? Okay, so those are our hair cells with the supporting cells, and the goal, take the vibration of that fluid and turn it into a nerve impulse, which it does, because when it moves and those cilia move, we exchange ions and we get the action potential on the nerve fiber. Yes, no, maybe. It's really interesting. That is one of them high-powered microscope pictures of the cochlea. So what we get is we get outer hair cells, okay? We get inner hair cells. The inner hair cells are the ones that synapse. The outer hair cells, they are very stiff microvilli, but because we're talking about sound, we call them stereo cilia.
You said when ions be exchanged.
When those ions move across the membrane, we start an action potential. Because just like other nerves of the body, where we had to have a little more of the pluses and the minuses across the membrane, it's the same thing here, just the structure is different. And so when that fluid moves and pulls on that cilia, ions get to rush in, and it starts the action potential on that nerve, which is kind of cool. And so these little hair-like projections that we're seeing in these structures, they refer to them as stereocilia, and that material that's laying over them is very gelatinous. It's not like water. Think about melted Jell-O. Have you ever seen melted Jell-O? Okay, and it just kind of wiggles. Okay, that's sort of how that fluid is in the ears. And it's the inner cells that are going to help us create the sound. So they're actually pretty cool when you're looking at them. These cells don't do any type of regeneration. you would think that, you know, because they do get a lot of exposure. Think about, I mean, pretty much nowadays, everybody's walking around with some kind of headphones in, okay? You would think that with so much exposure, these would maybe regenerate too, but they don't. What happens to them over time? They'll, what we call it, that the cells have died, but what happens, because of the structure and how these are, the cells are going to pick up a certain pitch, frequency, decibel, that sort of thing, okay? And depending upon noises that you are exposed to, like say, like for example, someone who may have worked in industry their entire life, they had the loud machine noises every day, okay? They will usually have a certain hearing loss. Maybe not everything, okay? But certain things they just won't hear. Because what happened is, because those cells had to work so hard every day at work all the time, the cell basically just gave out and it's just flat. It no longer works. So that's why you can have like complete hearing loss based on however much noise and stuff you had to pay attention to, or if it was something that you were just exposed to on a daily basis, year after year after year after year. And the cell just gives up. It just says, can't take it no more. Stops working. And that's what can happen with hearing loss. So, just like we've been talking about, that air, the movement on the air, produces the action potentials. We're going to see the nerve signals exit the inner ear, because they're going to be by way of the cochlear nerve. And when we begin to think about structure for hearing, there are lots of tiny, not lots, but there are some muscles, ligaments, and everything located in the structure. And their goal, protect our hearing. The way that the cochlea is set up, and when those movements begin to start, and we begin to put pressure, and like it's saying, we start with the tympanic membrane, which goes to the bone, the ossicles, which push on the perilymph, which put the pressure on the vestibular membrane, which pushes the endolymph, which pushes down on the perilymph, and all that sort of stuff. We have to have protection at the same time. The way that the cochlea is set up, the structure, the sound goes all the way around and comes back. And the goal of that structure, dampen the sound. If the structure didn't have that much to move through and it didn't dampen the sound, we would become deaf from our own voice. So that's how amazing that little itty bitty structure is in the inner ear. Those are the links. When I mentioned that the cilia was kind of a structure like this, okay, then each one had a link. So what will happen is, as that sound comes in and causes these to move, well, because this one is linked to this one, to this one, to this one, and it moves, every single one of them will move. And when it does, ions get to rush in, and we get to produce our action potential. That's pretty cool. probably will never think